Okay, hello again. So we're going to do some problems that are based on calorimetry from lesson 2. So a key thing with calorimetry is the Q system equals Q surroundings, or negative Q surroundings. That negative is very important. And we can rewrite this using the specific heat capacities such as this, right? So the specific heat of the system times mass of the system times delta T of the system equals negative C of the surroundings times mass of the surroundings times delta T of the surroundings. So here's a case where we take a spoon at 24 degrees, we put it in water at 85 degrees. They reach thermal equilibrium. So we're asked to figure out the final temperature. But before that, we're told that a student calculates the final temperature is 88 degrees. How do you know this is wrong? Well, we know it's wrong because the spoon's at 24 degrees, the water's at 85 degrees. So what's going to be the final temperature? I don't know. We have to do some math, and we will. But I know it's going to be between those two. I know it's not going to be 88 degrees, right? So that final temperature must be between those two initial temperatures. Okay, so let's do this problem at the board. So we're told we have a 45 gram aluminum spoon and water. So what we're going to do is we're going to talk about our system and our surroundings. Our system is going to be the spoon, and our surroundings is going to be the water. And so we're going to put that spoon into the water. And now the spoon, let's go ahead and say what we know about that. We know its mass is 45 grams. We're told the C, the specific heat capacity, 0.88 joules per gram degrees C. And we're told a temperature of 24 degrees C. This is 24. Okay, and what do we know for the water? We're told 180 grams. We're told the heat capacity of the water. Yes, 4.184 joules per gram degrees C. And we're given a temperature of 85 degrees C. All right, so now here's the point. This is the information we're given. We need to be very clear about what's what. If I confuse these C's, it's all going to go bad. So I need to make sure to call this the mass. We'll call this the aluminum. We could call it spoon. We could call it the system. Doesn't matter. And this is the mass of the water, C of water and T of the water. Now, let's look at these temperatures. Remember, at the very top it says delta T. Are these delta T's? No. These are initial temperatures. We need to find delta T's. Okay? And actually, we want to find the final temperature. Now, the key is that the temperature at the end for the spoon and the water is going to be the same, right? I put my spoon in there at 24 degrees. My water is at 85 degrees. So heat's going to go from the water to the spoon. Okay? And at the end, I don't know what the temperature is going to be yet, but the temperature is going to be the same. That's thermal equilibrium. Okay, so let's go ahead and let's start filling out what we know. All right, so we know C, M, and T, right? So let's just put this all here. So C aluminum times mass of aluminum times delta T of the aluminum equals C of the water times mass of the water times delta T of the water. Okay, so we have C's, we have M's, we don't have delta T's. So let's actually realize that we know delta T is always T final minus initial. So let's plug in some stuff. So 0.88 88 joules per gram degrees C. I'm going to put parentheses around there just to clarify everything. 45 grams. This will be T final minus 24 degrees C. And this is going to equal the same things but for the water. (180 grams) (85). And so I have this all, and same thing I do in class, I run out of space. It's going to happen if we were in a real lecture hall or here. Okay, so I have this. It's kind of complicated, but we only have one term, so we should be able to figure this out. All right, so first thing I'm going to do is I'm going to go ahead and I'm going to multiply these two together. So that's 39.6. This will be joules per degree C times T final minus 24 degrees C equals 4.184 times 180 equals 753.12 joules per degree C. T final minus 85 degrees C. Okay. Now I'm going to go ahead and I'm going to distribute all of these. Okay. Now it's a little bit of algebra. So it's 39.6 T final minus this times this. So that's going to be 950.4 equals 753.12 TF minus a bigger number, 6,064,015.2. And I'll show this again on screen so you can see. And now I need to rearrange this. I'll put that right here. So I will move this over here, or actually I'll move this over here. I'll move this over here. So what I'm going to do is subtract 39.6 TF from both sides and add 64,015.2 to both sides. This is solving for basically x, right? This is what you do in algebra. If you want a refresher, you can look it up or talk to me and I can try to find some. All right, I'm going to do this and that will end up right here. What do we end up with? We end up with 792.72 TF equals 64,965.6. I solve for TF, and that ends up being 64,965.6 over 792.72, and I end up with 82 degrees Celsius. I'm ending up with 2 sig figs because I start off with 2 sig figs. 2, 2. This has 4, 2, 2, 2. So my answer is going to have 2. Now, the last thing I should do is I should say, does this make sense? Notice what I said. I start off at 24 and 85. So does it make sense that they end up at 82 degrees? Yes. All right, let's just go ahead and show this on screen so you can see it a little more clearly, possibly, right? I called the spoon this system, water surroundings. Again, oops, doesn't matter which order, so I plug it in, plug in everything I know. I distribute the parentheses, so I end up with this. Then I solve for TF and I get 82 degrees. Okay, let's go on to video problem 2B. All right, so video problem 2B is a bomb calorimeter problem. Before we do this, let's just make sure we understand the difference between a bomb calorimeter and a normal calorimeter. In a normal calorimeter, such as a coffee cup calorimeter, I would just have some water in a coffee cup, okay? And then I'd have something. That could be a piece of metal, or it could be a reaction. And what's going to happen is heat's either going to go out or go in. And so the Q of my, let's call this a piece of metal, or actually let's call it a reaction because we're dealing with a reaction here. The Q of my reaction equals negative Q of the water. And so then I could go ahead and I could add in and I could say, okay, C, so the Q of the reaction equals negative C of the water times the mass of the water times delta T of the water. That's not the case here. In a bomb calorimeter is different because you have that container right here. It's a metal box or metal cylinder, and that is called the bomb itself. And so what happens is, when I have this reaction, there's still water in here. Let's say this is an exothermic. Some of that heat is going to go to the water, but some of that heat is going to go to the bomb itself, right? And so I need to take into account not only the heat that goes to the water, but also to the bomb, okay? And so in this case, the Q of my reaction is going to be negative Q of the cal, sometimes they call this bomb, plus Q of the water. And so I need to do that. All right, so in this problem, so I need to take into account both of those. In this problem, we know the big C for the cal equals 893 joules per degree C. And then C of the water equals 4.184 joules per gram degree C. Notice big C, little c, and the units are different. Why are they different? They're different because this already incorporates mass. This one doesn't. The reason it doesn't is that calorimeter, it by itself has a fixed mass, right? So that's already in there. All right, so in order to remember, this big C is Q over delta T. So if I want to figure out Q for the cal, it's going to be C cal times delta T. Whereas for the water, we're going to have an extra term in there. Okay, now I can plug those both in. All right, so this is going to be Q of the reaction equals the calorimeter constant times delta T of the cal plus, there's a negative sign there, C of the water times mass of the water times delta T of the water. All right. And I think we have most of this, right? So Q reaction equals negative 893 times delta T, 11.8 degrees C. Notice how the problem says water increases by 11.8 degrees C and the calorimeter. So that means both these delta T's are the same and they're both positive because they increase. All right, so that plus 4.184 times my mass, which I was told it was 775 grams, times this 11.8 degrees C again. This Q reaction, this is going to get me negative 10,537 joules, because this is joules per degree C, right? Plus 38,263 joules. If you don't know where these are coming from, don't just trust me. Do it on your calculator and see that it makes sense. You know, it's video, you can pause it, do it. Hey, make sure I'm right before you go on. And if something doesn't look right, let me know. All right, so we get negative 48,800 joules. Now, sometimes we can just leave it at that, right? In fact, this just asks how much heat, so this is a perfectly fine answer. But a lot of times we want to convert this to kilojoules. So 1,000 joules equals 1 kilojoule. And so this is negative 48.8 kilojoules. Okay, so this is the Q for the reaction. Now, let me go ahead and show this on the slides. Now, that negative sign that I calculated, what that means is that heat is leaving the system, right? And so that means 48.8 kilojoules are produced, right? When I do this reaction, I'm putting out heat, right? So it's produced. Okay, so we went over this in lecture, but I want to go over it one more time. All right, so this negative 48.8 kilojoules, this is for 3.12 grams. Well, what if instead of having 3.12 grams, what if I had 6.24 grams? Well, what would I get? I get twice the amount of heat. And so this is what we would call an extensive property. Extensive properties aren't that great. So what I can do is I'm going to go ahead and I'm going to make this intensive. And I make it intensive by just taking this value and dividing by the number of moles. So this is 3.12 grams of glucose. Glucose has a molar mass of 180.16 grams per 1 mole. So that means this is 0.017318 moles. This is from Chem 215. We can't forget about this. You're going to be doing this a lot. So make sure you remember how to go from grams to moles. Okay, I can take this value divided by the number of moles, and that's going to get me the number of kilojoules per mole. So negative 2,818 kilojoules per mole. This is what we call the heat of combustion. For every 1 mole, I get this much. This is nice because if I know I have 2 moles, I get twice as much. 3 moles, I get 3 times as much. I can use this for a bunch of calculations. And that's what we'll cover in lesson 3. All right, so I want to end this exactly at 20 minutes, so talk to you later.